scientists have found a planet that by the laws of space shouldn't even exist. And this isn't the first time. The universe in itself is such a complex and vast system that the second we begin assuming that we've learned all there is to know, it throws another surprise our way. Planets defying the rules we assume apply to everything out there are a key example of how just unpredictable space really is. Now, we are sure this raises several questions in your minds, like how is that even possible, or what does this mean for human life? That's exactly what we're getting into in today's video. We are sure you wouldn't want to miss the answers that will satisfy your brain itch. Keep watching to have your mind blown. One of the most fascinating discoveries scientists have made is exoplanets. What is an exoplanet? Let us break it down for those of you who may not be well versed in astrophysics. To put it simply, these are planets outside of our solar system. It may be a big trip to think about the fact that we aren't the only solar system or galaxy in that big outer space. Exoplanets orbit other gas giants like the Sun. Scientists were pretty solid about their discoveries in terms of how these planets are formed. However, a recent newfound potential host of alien life has forced them to rethink some of their ideas about planet formation. A new study reports that a young binary star system about 325 light-years from Earth is home to an exoplanet 11 times more massive than Jupiter, which resides in B Centauri. Known as B Centauri b, the planet is among the heaviest ever found. And combined, the two stars in B Centauri are 6 to 10 times heftier than our Sun. This makes the system in which a planet has been discovered by far the most massive to date. Researchers said B Centauri is also the hottest known planet hosting star system. Marcus Janssen, an astronomer at Stockholm University in Sweden, said in a statement that finding a planet around B Centauri was very exciting since it completely changes the picture of massive stars as planet hosts. Compared to our Sun, which has been burning for more than 4.5 billion years, the two B Centauri stars are about 15 million years old. Consider they are young pups in comparison to our big dog. What would seemingly make them unlikely planet hosts is the duo's combined mass. After all, the heaviest single stars confirmed to have worlds orbiting them are about 3 times more massive than our Sun, and the heftiest known planet harboring a binary star system contains 2.7 solar masses, according to team members of this study. Bolstering that bad parent assumption, the B Centauri system's heat and power is a force to be reckoned with. Researchers said that the main star, B Centauri A, with an estimated temperature of around 32,000 degrees Fahrenheit or 18,000 degrees Celsius, is a B-type star. That's hotter than any other known planet-hosting star. To put that into perspective, that's about 3 times hotter than our G-type Sun. Therefore, B Centauri b is blasting out lots of ultraviolet and high-energy X-ray radiation, which tends to disperse planet-forming gases and dust. Janssen said that Type B stars are generally considered quite destructive and dangerous environments. And so, it was believed that it should be exceedingly difficult to form large planets around them. But this newfound planet managed to buck all those odds. Using the spectropolarimetric high-contrast exoplanet research, otherwise known as SPHERE, which is installed on the European Southern Observatory's Very Large Telescope in Chile, Janssen and his colleagues discovered B Centauri b. In a feat the instrument has pulled off with several other exoplanets, SPHERE took a direct image of B Centauri b. The researchers used the analysis of the SPHERE observations to characterize the planet, which has other extraordinary characteristics beyond its enormous size and the mass and heat of its parent stars. Though nobody realized that at the time, the newfound planet was imaged by ESO's 3.6-meter telescope in Chile more than 20 years ago. For example, about 14 times farther away than Pluto's average distance from the Sun, B Centauri b currently lies about 550 astronomical units from the star duo. The authors of the study said that's one of the widest planetary orbits known, and so this immense distance may explain the planet's survival because it kept it relatively safe and removed from the radiation blasting from the core of the B Centauri system. The origin story of B Centauri b is unclear at the moment. It may have formed in the most common planet-forming process relatively close to the binary star via core accretion, in which dust grains in a protoplanetary disk gloom together to form rocky building blocks, which are then eventually brought together via mutual gravitational attraction. The study team members said the young world could then have been booted to its present location by gravitational interactions. It's also possible where core accretion is less viable that B Centauri b was born close to its current position, given the lower density of material out there. Though if it did indeed occur, it is a far-flung formation, therefore it may have involved a different method known as gravitational instability. Caitlin Crater of the University of Arizona's Stewart Observatory wrote in an accompanying News and Views piece in the same issue of Nature, stating that this top-down model requires that the mass of the protoplanetary disk be so large that it causes part of the disk to collapse on itself under the pull of its own gravity. When this happens, a small secondary body is created and starts to orbit the star. Crater went on to say that the gravitational instability mechanism also tends to create objects that are very large. In fact, they are so large that they fail to become planets. So when compared with the stars it orbits, this planet is small, thus making gravitational instability less likely than core accretion. In her opinion, perhaps it's just a planet similar to Jupiter, which was flung out to the far reaches of its stellar system through an interaction with the stars it orbits. To clarify the exact mechanism of its formation, a broad census of planets associated with large stars will help. Around the time Wolfson stumbled on an exoplanet, other astronomers were hunting for them already. In 1988, a planet matching Jupiter's mass was found orbiting an orange giant star about 45 light-years from Earth. A team of Canadian astronomers announced the discovery of Gamma Cephei AB. However, in 1992, the discovery was retracted as the team didn't have enough data to sustain their claim. In 2003, it was rediscovered, for real, when another group confirmed Gamma Cephei AB's existence. Importantly, the Canadian team hunted exoplanets using a method that involves carefully watching the spectra of light emitted by stars over time for a wobble in their motion known as the radial velocity method. These wobbles are indicative of the tug of an orbiting planet. Requiring long and precise observations is a difficult technique. Skepticism hampered scientists' ability to detect them, as astronomers at the time had yet to discover an exoplanet. Lisa Kaltenegger, director of the Carl Sagan Institute and a Cornell astronomer, said the exception was that the detectable planets around other stars would need an incredibly long time to be detected, or much more precise measurements, which were not yet available. Since 1992, exoplanet science has progressed tremendously because that is when astronomers successfully used the transit method. This method is done by watching stars for dips in their brightness as planets pass in front of them. It was used to discover HD 209458b, or Osiris. The technique has become incredibly fruitful for exoplanet hunters since then. Kaltenegger says that about 70% of the exoplanets known so far have been discovered by transit methods. Test missions and NASA's Kepler used the technique. Moreover, the James Webb Space Telescope will even be able to study and find planets with Earth-like atmospheres and transiting exoplanets to suss out details of their atmosphere. As precise as it is, Wolfson's pulsar detection method should have revealed many such pulsar planets by now. According to Wolfson, that's the thing. He's been engaged with a number of long-term surveys, which were to search for millisecond pulsars and then look for planets around them. They found nothing like the PSR B125+12 system, even if they found a few objects around neutron stars. Why the first confirmed exoplanet appears to be part of a one-of-a-kind system still remains a mystery, but exoplanet science is full of surprises because it's still so relatively young. Star systems may yet prove to provide a narrow niche because they were once assumed to be entirely hostile to life. Kaltenegger says if planets persist until it settles down in its white dwarf afterlife and can survive the demise of their star, then a new kind of planet is now on our cosmic horizon, which could harbor life. What this could mean for the future of humanity is hope. While this is all we have for you today, folks, stay in the loop about the latest space-related news by hitting that subscribe button and turning on the notifications by clicking the bell icon. Sound off in the comments about whether or not you think these exoplanets could in fact harbor life and propose new beginnings for humanity. Until next time, ciao.